tell you what my particular job was in the space program in terms of putting a man on the moon. But in order to do that and give it some context, I'm going to give you some history or background of the complexity of putting a man on the moon and what was really involved. And then I'll describe a little background history on how I got down there and what was actually done and the accomplishments done by NASA in the space program. So I'm going to give you a brief history of that, a brief history of my involvement, not necessarily in this order, the logistics involved, the people that I interface with in terms of the German rocket scientists. My goal, which was, and their goal, finally my contribution, and some other tidbits of little pieces of information. So, the goal as set by President Kennedy in 1961 in May was to put a man on the moon in 10 years' time. Ensure that there was redundancy enough that it wouldn't, that we put somebody on the moon and get somebody back. And that way they would simulate and test everything that went into doing it to guarantee, which was an enormous effort. What did the guarantee the launch window? Because the launch window determined the minimum amount of energy that you needed to get a rocket off of the Earth's surface, into orbit, into translunar orbit, and back again. Because the rocket only contains so much fuel. And one of the things that I guaranteed that with 40-mile-an-hour winds, as the rocket was taking off from the gantry, 40-mile-an-hour winds would not push the rocket into the gantry and destroy it. So those are the things in general that were involved in it. Now the facilities are spread all over the southern part of the United States. The NASA established two space centers. Goddard, which was an American center. Goddard had been in rockets for years in the 30s and the 20s. And of course that was the German, had put them in Germany that was making rockets in World War II, of which von Braun's team was captured by the Americans and another team was captured by the Russians. So the Russians had a rocket team from Germany and the US had a rocket team from Germany. And there was competition between the American rocket at Goddard and Redstone Arsenal, Huntsville, Alabama. And unfortunately, the American rockets were not very successful. And NASA then turned to von Braun and Redstone Arsenal, Huntsville, Alabama. So they selected many different industries to do things. Boeing was assigned the primary integration contract for the entire mission, and they were responsible for building the main first stage. And that was done near New Orleans in Michoud. NASA then bought the facility at Cape Canaveral to build the vertical assembly building and launch pads 39 A and B. And then they selected North American to build the stage 2 and Douglas to build stage 4, or the lunar module and the command module. IBM was involved in building all of the computer control that controlled everything between the rockets. So IBM was a computer manufacturer at the time, so was Boeing, so was RCA, so was Burroughs, so was Computer Control Corporation. So everybody at that time was in the process of building computers, big computers as well as small computers. Boeing happened to be an IBM site, and that's how I got involved with the IBM side of doing things. Now the most accomplishment that was ever done was the organization by NASA to basically integrate what everybody was doing and make sure that things arrived on time and were able to be tested and integrated appropriately. This, to me, was the biggest accomplishments of basically an organization, of building a huge organization structure that could basically manage every little item that went into the rocket. And why I called it the pyramid building days of the United States, because it involved 400,000 people to build one rocket, to put one man on the moon, and then they dissipated. So things got from New Orleans by barge into the Gulf of Mexico, up the river, up to Huntsville, where they tested the primary engines. And when we were in Huntsville and they tested the engines were mounted into the side of a mountain, and the entire area shook. Other barges carried things through the Panama Canal from Connecticut all the way up to Huntsville for testing, and eventually to Cape Canaveral. And some items from Douglas were actually flown on top of a Boeing Guppy 707 at that time. So these were the logistics. Stuff that came out of California, went up via barges up to Huntsville where they were tested, brought back to New Orleans for refurbishing, and eventually got to Cape Canaveral for assembly. So there was a big management process in doing that. Now this rocket weighed about 6.3 million pounds. Most of it was liquid oxygen, kerosene, liquid oxygen, liquid hydrogen, liquid oxygen, liquid hydrogen. So the most error-prone in this entire thing is in the hydraulics. How do you feed liquid oxygen? How do you feed liquid hydrogen and kerosene into the engines and not have a failure of some sort? So,
or fire, right? Or explosion?
Not an explosion. The majority of electronics was done up in the LEM, Lunar Excursion Module, and the command module that basically orbited the moon for the LEM. So that was and all of this does not take long to get up into the atmosphere. This is at the first stage, 3 minutes and 12 seconds. 2 minutes later, 42 seconds, it separates and is on to the second stage of the rocket. Second stage of the rocket, 9 minutes and 9 seconds. After that, it gets rid of the escape towers of the astronauts at that point. And they're up about 19 miles. All right. Third stage, 11 minutes after blast off, it's ready for a translution or injection. Once it goes into the proper orbit around the Earth, 2 hours later it fires and it's on its way to the moon. So you see, it's not taking very long to establish getting things moving towards the moon. So that was the complexity of basically the timing. I would say the rocket engines that went into it, all the electronics in terms of timing, because they're not being controlled from the ground, it's controlled by all of the instrumentation and all of the computers that are on board. And one of the things that was done was, wherever they could, they built in triple redundancy. So every circuit was triple. There was 3 computers there to basically vote. If 3 computers had the correct agreement, that was the agreement. 1 didn't and 2 did, they took the bid from the 2 computers as being correct. So that was now the history of me is 57, I was still in high school, but I was building rockets. I was actually the chemist. I was the one that designed the rocket engines for our rockets. When we graduated and went off to college, that's when Goddard and Marshall Space Flight Centers were established. And there's Kennedy's speech in '91, Voting Rights Act, all the civil rights aggravation. I graduate, and as we are driving down to Huntsville, Alabama to take my job, the civil rights workers are dug out of the levee. And there I go to work for Boeing as the primary contractor integrator for the Saturn V. So that's my brief history of how I got involved. And this is what welcomed us to Huntsville, Alabama. All right, the key people, of course, was von Braun. My interface was with Arthur Rudolph, who was given the primary job of doing the integration and testing to ensure that the Saturn V Apollo program would be successful. I used to sit in on the management teams and in the meetings. I was not allowed to say a word, but when they made a request, they would look to me and see if I said yes or no in doing something. And George Irwin Miller was the associate director. It was his responsibility to make sure that he agreed with all of the testing that was going on. Rudolph wanted to do a lot more expensive testing throughout the entire stages. Towards the end of the program, Muller bypassed Rudolph and did not do all of the testing that Rudolph wanted to do. All right, now this rocket, its materials were basically all brand new materials, all new electronics. Nobody knew things about how long they would last. What was their mean time to failure? Was it 6 hours, 6 months, a year? They don't know. A lot of guesswork went into supplying information to everybody as to how well the components would operate and how long they would operate without failure. And that all went into simulating exactly down to the component what would fail and what wouldn't as a high probability. Then we have to know what are the steps to assemble this? You know, what equipment do we need? What types of physical equipment? What kind of bay experience? Is it in the vertical assembly building? Do I have to pull it out of the vertical assembly building and bring it back to a factory someplace? Or can I just disassemble it, use equipment there? How many people do I need to do this? How long is it going to take? Is it going to interfere with doing something else? All of these questions had to be asked because they had to be simulated to find out the impact if anything failed. Can I do things in parallel? Is it serial? Is it going to impact the launch window 3 months down? Is it going to impact the launch window 2 hours from now? So those questions were, and which were the most critical components? Do I replace the entire thing? Can I take something apart and replace individual components? So these are the questions that were asked, and somebody had to come up with a way of asking these and realizing some impact to testing all of this. So a typical simulation information would be that the Saturn V, the main engines were 1.5 million pounds of thrust each. 5 engines, 7.5 million pounds of thrust. They do not sit rigid. As soon as you fire them, they vibrate. How much do they vibrate? We'll say it vibrates 1 degree off of center. If it fires 1 degree off of center, what is the force does it place on the rocket? Is the rocket going to bend, fold, and break apart? Things like that. Again, a thruster computer fails in testing. What failed in the thruster computer communications? We go down, and statistical analysis and probability tells us either a subsystem or actual component that is the high probability of failure based on the numbers supplied to NASA about the mean time to failure for these components.
Correct.
So I happen to write the software to basically take all of this information in, design also a graphical interface so that you can program it by word or program it by picture, by assembling it and putting these together. And typically take the subsystem and put in all of the information about it, all of the statistics about the mean time to failure, what type of facilities were needed, how long does it take to assemble something, how long does it take to disassemble something, how many people are needed, where are the people, someplace else, do we have to break them away from doing something else, delay something, all of that information. And this became a programming language, which was, I didn't model, all I did was provide the software for the modeling. Every engineering group that was responsible for a particular system or subsystem then modeled their system with this software and came out with statistics about it. Graphically, it might look something like this, but not so simple. It would be maybe 4,000 or 5,000 blocks like this per subsystem.
So you invented that, RD?
Yes.
Wow.
It was modified from the original IBM software that was very limited. They did about 12 blocks on the screen. I did 5,000.
Wow.
I rewrote the system for a lot more different functionality. Where am I? All right. So those are some of the statistics. Some guesstimates were made, like we're using barges to transport all of this on rivers with bridges and drawbridges. And one of the questions that I asked them, what is the probability of a drawbridge failing closed? And nobody knew anything, but one director said, I have never seen a drawbridge failed closed, only open. Yeah. So we didn't have to worry about it. All right, and NASA or Rudolph or everybody really wanted a probability guarantee of a launch window of 99%. They wanted almost 100. And we could not guarantee that because the launch director, at his discretion in the last hour of setting up a launch, could order whatever test he wanted to do. It was in his head. It was never written down, I'm going to do these tests. It was, I have a series of tests. I don't know if I'm going to do any of them or all of them. So we only guaranteed it to 97% probability. Here I am at work. This is IBM had produced a graphic system that was being used by General Motors and IBM. I had reprogrammed this entire thing. It was used for the simulation work, and it was also used for the data reduction of the telemetry tapes that were brought back from the launch. And I was written up along with Boeing about my work and how much time it was saving NASA at the time. That's the only article I have left of it. And I did receive my accommodations from them. So, the Saturn V was the largest rocket ever built at that time. It weighed about 6.5 million pounds. When it first took off, on its first flight in '67, earthquakes were recorded all along the eastern seaboard. That's how powerful it was. And they were the most powerful ever built for the size of the rocket until the Russians. Their latest rocket produced about 10.5 million pounds of thrust, but it has never delivered the payload that we've delivered to the moon. So these things were big. I just want to show maybe. The vertical assembly, these, in comparison to people's size.
Wow. The size is unbelievable. It's Lord.
In the future, they see fossils.
The vertical assembly building could actually hold 4 Saturn V's simultaneously. That's how big the building was. And here's a newsreel clip of basically how big this was.
It's an interesting sight.
I just wanted to say, my cousin was project leader on the trawler.
I was moving this rocket, an entire rocket weighing 6.3 million pounds, 3 miles per hour to launch.
How tall is that compared to the Empire State Building?
Hmm?
How tall is that compared to the...
Third.
About a third, so it's 363 feet. Right.
Cousin was there 2 years in charge of that transport.
Well, there's the vertical assembly building. This building was so big that you could put Yankee Stadium on top of it. And it's so tall, like the Blimp buildings, that it had its own atmosphere. It could rain inside even though it was sunny outside.
Artie, where was this building in relation to the launch site?
It was just a couple of miles from the launch site. Here's the building, the launch site, I think was,
Okay.
so with triple redundancy and a lot of guesswork, built by the cheapest bidders in the world to do this project. 15 Saturn V's were built. Every single launch was successful. We had some problems out in space with some failures that were corrected. Everybody was saved. And one of the reasons it was, which I forgot to bring up, is we simulated every single subsystem. So if anything went wrong, you saw in the NASA control room, every single one of these guys is responsible for some part of that rocket. And they had their book open because everything was simulated in the book. Everything is written down. Every component was there. What component was the probability of something failing? So you see, when you see everybody sitting down with these pages and pages of booklets on every single desk, everybody's responsible were one of the subsystems that was simulated and all of the information gathered about it. So when we had that failure in the moon where the three astronauts almost did not come back, it was because they were able to look at every single component that was there and come up with an engineering problem to basically circumnavigate that. And the most critical part of that entire mission when the engines blew up was re-entry. Because you had to re-enter at a certain angle. If you didn't enter at a particular angle within 2 or 3 degrees, you either bounced off the surface of the Earth, the atmosphere of the Earth, or you went down too fast and you burnt up. And that's why computers were being used to basically navigate all of this. But they did not have a computer to do that. They had a pilot, very experienced pilot. They were able to see the stars. He was able to look out of a window, and they told him exactly where the star should be in the window, that he would have the proper angle to follow his retro rockets and enter the Earth's atmosphere without burning up.
That was Tom Hanks.
And early on, a little statistic is when they first started testing things and they would throw an astronaut suborbital and he would come down and the ship would pick him up, and you'd say, so how did he get 600 miles off course? He was supposed to be here in the Pacific, but he landed 600 miles away. Well, somebody programmed that there were 24 hours in a day. There are not 24 hours in a day. There are 23 hours, 56 minutes, and 4 seconds. That's the difference between firing the retro rockets at the wrong time. So, in a nutshell, that was what the space program was, as briefly as I can give it to you. What was accomplished, and what thing I did with the other 400,000 people.
Very nice.
Any questions? Yeah, I've been there.
Artie, when you started off, your data said that Sputnik was 59,
57.
57, whatever.
Yeah.
Were you privy, or did the Russians share information that was helpful?
No,
Not at all.
not at all.
Okay.
Did you guys give any helpful information to the
I
Russians?
know. But
Probably.
Could you repeat this question?
The United States give information that was helpful to the Russians.
Yeah.
Overtly, I don't know, but probably, yes.
that's,
Jack wanted to know how many Jews were involved in this. I would say a handful. I mean, we went to services in Huntsville, Alabama. There were probably less people at the services than are sitting in this room. One of the people that was assigned to do an assessment of whether this would be accomplished was a Jew, and they made an assessment that it would not be accomplished until 1971, and their report was attempted to be suppressed because it was so negative a report about the program, because it was an impossible program that miraculously really fit together. Look, there's been no other, I would say, no other rocket that has had all of its rockets that were ever built was successfully launched without a hitch. Everybody else has had problems, one or another. The Russians, X-Space, whatever, everybody has had problems. But the Saturn V never failed on takeoff. It had 2 problems out in space, but it never failed in taking off.
Well, thank you for being responsible for a lot of it.
Yes.
Because this was one of the first, you know, of the thing that's unknown, how many levels of approval do they have above the people who made the decision and get approval above them? Any?
That I was such a lowly engineer, grade engineer at the time, even though I was doing most of the work. I never got higher than, I would say, level 2, a level 2 meeting with anybody. Anything else was higher than that, I never knew about it.
Well, did the higher people above you, did they know anything?
Yeah, the guy who was in charge of Boeing was a graduate, a PhD in electrical engineering or so, and had served in the Air Force. I mean, these were technical people. These weren't, maybe on the government side, they weren't technical, but within the program itself, they were all technical people. But, it might have been promoted to their level of incompetence, but anything else?
When we had that horrific accident where the thing blew up and there were how many people were killed, what failed?
What failed was the atmosphere that they were using. They were using a pure oxygen atmosphere within it. So any spark that would show up would ignite everything. You put anything into they made a mistake. They started using a pure oxygen atmosphere for the astronaut, which was wrong. And then they switched completely to a controllable atmosphere.
So that happened at the launch pad, right?
That happened in suborbital. That was suborbital stuff. That had nothing to do with the actual. The first test was in 1967.
Yeah.
The actual first launch to put a man on the moon was June
69,
1969.
July 20th.
So there had been at least 7 or 8 launches prior to that for testing.
They were all Saturn V.
And